Thanks for having us. It's an honor to be here with you guys. We'll go ahead and get started. Short window here. To really start the presentation, I want to set the groundwork that fiber reinforcement can be used in many different applications. With 30-minute window, we need to kind of narrow that application. While you can use it on columns, post-tension structures, spandrel panels, and vertical shear walls, we're really going to be concentrating on twin T structures today, twin T stems, and parking garages. So the first thing to recognize with FRP is that there are many different types of FRP that can be used, and understanding which FRP assembly you're going to use is going to be one of the first steps, whether it's glass, an aramid, basalt, or a carbon that you're going to be using in these environments. And understanding if you're doing multiple wraps, single layer wraps, multi-directional assemblies, depending on what the needs of the structure is. So the first thing you really want to do on one of these projects is, get the team together. Understand your strengths and weaknesses, and make sure that you bring the right team members into these projects to ensure that you're going to get a successful installation. Really, that's why we're here, right? Is to further develop our team, further understand who we need to work with, to make sure that we get a successful completion on these projects. We prefer to immediately, when we assess one of these structures, bring in the right engineering team. And from there, we can work with that engineering team to really run through those investigative openings, run through the needs of the facility, and then really provide a feasibility study to the owner. Make sure that this is something that's going to last for a long time. Make sure that it's something that we can actually do in that specific structure that you're working on. And then really look at the benefits from a contractor standpoint for the owner, right? Understand the owner's needs. Make sure that you are putting the right repair in that is going to accommodate the needs of the facility and the ownership group that you're working with. So the project that we're specifically looking at is a 2-acre facility. That's 6 stories, 3 below grade, 3 above. The facility was 99% full, 99% of the time, and it was a healthcare facility during the middle of COVID. So as you can imagine, there is very little room for impact to the facility, and schedule is absolutely everything to them. It was a twin T construction, and it was a double helix garage, which really limits a lot of the movement, single entry, single exit into the facility. And not to mention, most of the people driving in there are already nervous, scared. They're in a bad environment. They're in a facility that they really don't want to be in. A lot of the repairs that we were doing were horizontal and vertical concrete repairs. We did quite a bit of fiber reinforcement, and I'll let Tami dig into that a little bit deeper here in a little bit. But this all leads to understanding, once again, the needs of the facility that you're working with and the high standards of functionality that they absolutely have in that type of environment. And from a contractor and engineering standpoint, make sure that we're accommodating them to the best of our abilities to keep business rolling and to keep the patrons of the parking garage coming in and out. This was really the only parking, because it was a very dense area. It's the only parking for the facility. There was no street parking. There was no other parking structures. This was their sole source to get the patrons in and out of the hospital. With that, the first thing that we really do on a lot of these, especially when you walk into some of these structures, is you're going to get emergency shoring in there. Well, that emergency shoring immediately has a cost impact to the ownership group. And that bill starts running every single month, right? Now they're also losing revenue. This facility specifically was not a revenue generating facility. Other facilities very often are revenue generating facilities. And so if you have shoring towers everywhere throughout that parking garage, that ownership group is not only paying you for the shoring, but they're losing significant revenue on that. Also, schedule impacts. By the time you're putting shoring in there, you're adding days to the front and back side of the project. Not to mention, like we were talking about, this is a medical facility, so these people are already, worried or in a different frame of mind when they're going in there, and they get to see shoring, which, let's face it, is not the most beautiful thing you've ever seen when you pull into a parking structure. So that immediately hits them. And then last but not least is the life safety component, right? At the end of the day, they're in the hospital or they have somebody in the hospital, and we want to make sure that nobody else is going to end up in that hospital. So with that, I'm going to let Tami take over and touch base on a couple other points.
Thanks, Jake. Oh, sorry. Okay. So as Jake was mentioning, life safety is absolutely critical in these parking garages. And as engineers, that's really kind of our main focus point when we first get called out to look at a structure. So in this particular case, we were called out to do a peer review of a previous engineer's report. And that report was focused on 10 items, and only a few of those were double T stems. And they were kind of spread all throughout the garage. So as we were walking to all 10 locations, we had the opportunity to put eyes on the rest of the structure. As we were doing that, we found significant deterioration throughout, ultimately resulting in 70 double T stems that we recommended to be repaired. And based on our visual observations, we were kind of estimating that 42 of those stems would need supplemental strengthening. And as you can see in the photo on the right there, this was a condition where we had a chunk of concrete being supported by conduit, which we all know is not a structural support. And so this was one of the locations we recommended immediate temporary shoring to get everything safe while we could proceed with our design. As you all know, that sometimes takes time to work through the design drawings. Also along with the investigation phase, so this is the phase where we're really just trying to gather as much information as possible about the structure and how it was built. So we always want to ask for original design drawings. Sometimes we can find EOR drawings. A lot of times precast shop drawings are hard to come by, especially those piece sheets which show you how the reinforcing is detailed within the member. So for example, the diagram on the bottom there shows pre-stressing strands and just one layout that there could be, but there are many different patterns. So you can have your pre-stressing strands going straight through the member, or you can have them harped where they come down at a point at the middle. That's what this example here is showing. You can try to determine that using GPR. That's often not very accurate, and it just kind of looks like a blob of steel. X-ray is really the most accurate non-destructive testing method to try and figure out what your pre-stressing strand layout is. But a lot of times we find the owners don't want to pay for that phase of the project, so that can be a challenge. What we really like to do in that case is push forward getting the shoring installed and doing a select demolition phase. That's where we can have the contractor come in and chip out the section, and we can get a good idea for what's embedded in there. And then the figure on the right that I have is showing an example of a DAP double T stem. So these, whenever you have a DAP, that should be a kind of a red flag where you know this is a member you need to treat as a special case. There's been studies done by PCI that have shown some of the older reinforcing layout in DAPs have been found to be non-conservative. So those are items where you kind of need to stop and slow down and try and gather more information. So getting into the repair options a little bit, you know, ideally we would be able to pour back with concrete only at a double T stem. this is always the best case for schedule and cost impacts to the owner. So the photo on the right I have here is an example of a candidate for just pouring back concrete without structural strengthening. You can transfer your loads back through bearing. You have started to expose some of your pre-stressing strands, but it's only really for an inch or two directly over bearing. And then sort of our middle case would be where we get into FRP. That we're going to get into that a little bit more in further slides. But also considering the photo on the right, sometimes you're restricted by geometry. So you can imagine trying to get in cistered steel channels on the side of these double T-stems would be challenging, and Jake can probably tell you more about trying to deal with the challenging engineering designs. But so this would be an FRP candidate here. And then finally, our final case that we consider, at least for this presentation, is our T-stem enlargement. So this would be where we start to debond our pre-stressing strands for several feet past bearing. And because we've now lost that pre-stressing force, we can come in and put in stirrups and mild steel to try and turn it into a mild reinforced section. Okay, so getting into the meat of how do I determine if FRP is appropriate. These are a bunch of items that need to be considered. So first of all, where are we located in the structure? Are we at the roof or the floor? What kind of loading do we have? Are we under fire truck loading? Do we have snow load? These types of considerations can kind of clue you into the fact that you may have a different strand pattern at these locations. So you need to consider all those different cases. DAPT versus non-DAPT, we kind of hit on that previously. And then really one of the biggest ones is the number and length of strands that are exposed. So the further you get away from bearing, the more of your pre-stressing force you lose. And that needs to be considered not only along the length of the member, but also along the height. So I'm sure many of you in the room have seen funky geometries, and we're always trying to keep as much of the native material there as possible that is in good condition. Obviously, all the unsound stuff needs to come out. But so just kind of thinking through some of those different patterns and how does that affect the loss of pre-stress. When you see welded wire reinforcing within a double T-stem, it's important to note that this is structural. Sometimes that's thought of as non-structural reinforcing, but when you're in a double T-stem, we engineers are counting on that for our shear capacity. So you always want to try and chip as delicately as possible, and really we're trying to maintain the crossbones because that's what provides us with the development length that we need. And then finally up here we have the fire loom case. I'll go ahead to this slide here. So the picture up here kind of suggests we're talking about fire, but really the top two equations that we have to be able to meet are for checking the structure without the FRP on it, and it's the top two are not related to fire, so I just want to be clear with that. That's at room temperature and is for just general operating conditions in the event that the FRP is to be damaged in some way. So that could be due to vandalism, some sort of impact, really any other way that the FRP could be debonding. So we need to be able to meet those equations, and you can check it to see if you can meet the contribution due to concrete alone. If not, then we need to consider adding supplemental shear steel. And notice these are phi RN equations. So we have to check shear as well as moment. The moment case is the one that we find is challenging to try and meet. And this is kind of a difficult thing to wrap your brain around sometimes. I know it has been for me. We always think of a simply supported member as having our critical moment section at midspan. And that's the case for mild reinforced members. Once you add the pre-stressing in there, it adds a whole new element to that. And you start to see critical sections at the end of where you debond those pre-stressing strands. So that's something to watch out for, because as engineers, we don't typically think of moment as controlling near the end of a member. So here's some photos just showing, on the left, this was a candidate where we wanted to use FRP. So we put in supplemental number 3 bars that were hooked at the bottom and at the top. In this case, that was easy for us because the flange also came out. So we had these in here alternating, and then we also added in mild bars in here to meet that moment case. That's something I'm still scratching my head as far as how Jake's team got those bars in there.
That's good.
Somehow they did some gymnastics there. And then this is just a photo showing the installed condition. And so that kind of gives you a view of how to determine if FRP is appropriate from the engineering side. There's a lot more that goes into this as far as design, but we don't really have time to get into it today. So I just wanted to show you a photo of it installed. We tend to gravitate towards using discrete strips instead of continuous FRP. This allows the system to breathe if you were to get water in through the joint and tracking over and down. So I think I'll hand it back to you, Jake.
Alrighty. So enlargement is often twice the cost of FRP. Now, granted, all of us contractors in the room would definitely agree with this photo. I don't think our owners do. and so really at the end of the day, the one project is fantastic, but with these clients, we really are looking to go do another 10, 15 projects with them, right? So making sure that we're giving them the most cost-effective approach on one of these projects is going to be key. When I say it's often twice the cost, it's also over 1/3 the schedule reduction, or sorry, it's 1/3 the schedule reduction for an FRP installation versus an enlargement. FRP really offers the majority of that reduction in the labor cost. The material cost on the flip side is a little bit more expensive than the concrete and rebar, but the labor savings is significant. One thing I really want to point out with FRP is that it traditionally is a very front-end loaded schedule impact to a project. So pre-planning for FRP on a project is going to be absolutely key, because the design and engineering that needs to go into it, and it needs to be specific for every project. And then once again, yeah, FRP installation is roughly 1/3 of the enlargement cost. This is a perfect example of what this parking garage looked like every day. So as you can tell, schedule is absolutely necessary, and minimal impact to the facility is necessary as well. One of the other major impacts on schedule is testing for the FRP. So I'd like to point out the black circle on the top left. That was actually a failure, but it was a failure because the puck pulled off of the carbon fiber, and we didn't actually get any host material. So it was really actually a failure between the testing mechanism and the FRP itself. But if you don't have a positive result with host material, then it's absolutely a failure. The big point with this is that the testing is done on site, and it's done extremely quick. We're not waiting for breaks. We're not waiting for third parties to get involved at a different facility. It's on site after a couple of days of installation, and we can immediately roll with removing the shoring and getting the shoring to another location for repair. So there's other benefits to the fiber reinforcement, and one of them that is really important is the corrosion mitigation that it can offer in certain applications. We've tested a lot of the epoxies over the years to see what the reduction in corrosion mitigation is, and then as Tami pointed out earlier, they're doing wraps, not full wraps, but smaller wraps to allow moisture to escape the system. But in like column applications, you can really prevent a lot of chemical intrusion from getting in. Another benefit is the immediate strength. So whereas traditionally we would need to wait 7 to 28 days to get our brakes back, depending on how they come back, to get the scaffolding or shoring out of the facility, with fiber reinforcement, we can traditionally get all of that shoring after the repair's out within 7 days. It's very, very quick. Low profile. Most people will absolutely never know that there is a carbon fiber that repair there if they're looking at it. They just wouldn't know how to recognize it. Whereas in an enlargement or adding steel to the end of a twin T, everybody's going to see that something different is occurring at this one location. Whereas with a fiber installation, you don't necessarily see it. You can put coatings on it to get it to match. Those coatings also offer UV resistance if you need it. Sustainability and longevity. At the end of the day, the amount of waste that comes out of a fiber installation is insignificant. There's relatively nothing left after one of those installations. Whereas once we get done with all of our form wood and everything else from an enlargement, we start to have significant waste from those enlargement repairs. And then once again, we kind of talked about the discrete nature of it. But it also helps with head heights. In other applications, in enlargements, we've had to change the head height of a parking facility, whereas we don't need to do that with a fiber reinforcement. As we talked about, this facility was a facility that needed a constant access and parking for the patrons. So with the fiber reinforcement on this facility, once again, quicker test results. We're able to move through the facility with less impact. We weren't taking up a full city block with laydown areas, trying to get our materials and equipment in, pallets of material versus a couple pails of material and a couple rolls of material is significantly better for this type of facility. So the reduced laydown area was a huge consideration as well. So with that, we have a couple minutes for questions. Looks like we have 5. Any questions?
Just out of curiosity, the double T sections that I saw a picture where you were strengthening a larger length of the double T. Was there anything like the design strength efficiency in addition to the corrosion and some issues you saw at the end? Why did you need to strengthen that larger length of the double T?
Yeah, so I believe that one had to do with heavy loading at the level above, as well as the length of strand that we had debonded. And so not only do you have to look at the length that you've debonded, you then have to consider there's a transfer zone past that to get the pre-stressing strand up to full strength. And on that particular one, because we were repairing at both ends, it grew so much that it basically met in the middle.
Any questions?
I noticed that you did bond strength testing on the FRP. Do you find it necessary to do tensile strength testing on the prepared surface on the substrate? Or did you just go right to bond strength?
So I don't believe that we did testing on the substrate in this particular case. This is something that's being worked through. I know it's clearly defined in ACI 562, which is adopted in some states but not in others. So I think that the industry is definitely moving towards where that will be become a requirement on all drawings. We didn't have it in this particular case. We relied on pre-pour inspections and good surface prep prior to pour back.
We did test the repair mortars as well, though. So at every repair location, we would do a separate pour off for that specifically. So we were testing both host and repair mortar.
Yeah, I was referring more toward the preparation of the substrate for the FRP.
So really what you need to do is you need a sound substrate to apply to. So sounding the material is critical. If there was any honeycombing or something, that would need to be addressed. But yeah, that test is not usually required unless there's some sort of visual indication that the material isn't sound.
I just noticed that you had discrete strips instead of continuous strips. Was there a reason to do that, and to have to increase the density of the CFRP as well, or what was that?
The reason is so that it allows the system to breathe if we start to get moisture in, because that can be a problem if you're doing a continuous strip and you get water in. The freeze thaw cycles can start to debond at the top. And sorry, was there a second part of your question?
Do you have to increase the density of the CFRP itself, or how do you put?
I don't believe we increased it. I believe we only had one layer, but you just need to work through the proper spacing of the strips, and that you work through that in the 440 equations.
Once you release the stress on that pre-stress table, could you explain again a little more about how you develop the strength of that stem?
That's a very deep, involved answer. I don't know that I have the appropriate time to address that.
But isn't that the like $64 question?
We could probably dig into it out back.
Yeah.
Got time for one more?
So the photo where you're showing the project, it looked like that was a mock-up over the course of that project. Is there a frequency that you need to test the bond stream?
We tested every day of installation. So we basically identified it as, these specific T-stems were repaired and poured. So we poured it all in succession, and then we wrapped all in succession. And for every one of those, we tested both the repair mortar, host material, and wrap at each one of those, so it was daily. But that's all we have time for. If anybody has any other questions, we'll be out back. Thank you.